Okay, was the first, I guess the first circuit was an inverter. So how would this go? Start off what? Yeah. Let me see if I can make this bigger. I'll just make it. I'm sure I can. We start off high. Right, get right here. What should it do? Low, high, right there. Then it goes what? Low. Are we okay? Are we okay? This is a, what do we call this guy? Negative north, which is this guy right here too, right? So whichever way you look at it, the waveform would be the same. Y'all understand that, right? Those are the same gates. It's just one's drawn in negative logic symbol and one's using positive logic symbol. So you look at any load, so we can come up here and just highlight loads. So did I get all of them? So any low should give me a high, right? So that'd give me a high right here. That'd give me a high right here. It should take me through here, right? Are we okay? Huh? No, it's going like this. Any low would give, yeah, that's what that gate right here says. Any low on an input would equal a high on an output.
Okay, so right on the picture.
Right here?
Okay, go down. You want to like the way you went, right? Okay, go like.
Oh, I'm
right
sorry.
there,
Right here.
high.
Yeah, I missed that. Right here. Good call. Any more? Is that okay? We okay? Negative north. No, not for this symbol right here. This is any low equal to high. That's right. No, yeah, that's wrong. Good call. I need to correct that. And we look at the symbol. I need to do that right now. And we can look at, so we can look at keys, but what I want you to do is look at the symbol. And if you see this symbol, what are we going to say? Now we're going to start off, since it's got that curve, and y'all probably, since it's got that curve, we're going to start off at E. Oops. So if I see this curve right here, right, without the ghosting, if I see this curve right here, I'm going to start off with E. And then I'm going to look at the inputs. If the input's got bubbles, I'm going to say what? Low. And then I'm going to look at the output. If the output doesn't have a bubble, I'm going to say what? High. That's what I want y'all to look at, right? Is to look at the symbol and let the symbol tell you what it looks like. So over here, if I saw this symbol, I'd start off, since it's got this shape right here, I'd start off and say what? Oh, I'll look at the inputs. I say all what? highs, yeah, because that equals a low. That's exactly right. So the symbol tells you what it's looking for. I know that was a mistake, but this is what I want y'all to just be able to do what? Look at the symbol and come up with your any. And that the any's and alls to me is a lot easier than truth tables. It is. It is. It's a lot easier than truth tables. Because truth tables would vary depending on your number of inputs. So here I would have 8. If I add one more input, that would give me, here I'd have 4. One more input would give me 8. Another input would give me 16. But it don't change any high to get a high, right? You understand that? Because that makes it so easy to troubleshoot when you get these things in your head, right? That makes sense? So this guy says any low to get a low. Yeah. Guys, that's exactly the way I taught it in class, but it always amazes me. People say, when you give out the worksheet and they say what? Oh. So we're going to mark off, and what I do is I just look at the symbol and what I try to highlight is what the gate is looking for. Now this is what? This is an AND. But you can roll those things around too. If you say any low gives me a low, just roll it over and say all. So all highs will give me a high. Does that make sense? So any low will give me a low. So I'll start over here, right? So I get right here, and I go down, and then I go all the way over to right here, right? Then I come over here, right to there. Oops. Now, if you look at this, it's also saying all highs give me a high. That's exactly the same gate. It's just how you look at it, right? You understand? We okay? So this gate says what? Any high equals a low. So what I'm going to do in this guy is I'm going to just identify highs. So any high equals a low. Am I missing? That's exactly right. If it was drawn using the negative logic symbol, right, Brian? So ain't that neat the way you can just roll them around? So you could figure out what the gate is. I mean, because when we buy them, when we buy the gates, we buy them according to their positive logic symbol. We don't buy them according to their negative logic symbol. When we say positive, negative logic, what are we talking about? We're talking about the active state of the input. It has nothing to do with the active state of the output. So positive logic has high active inputs. Negative logic has low active inputs in the basic gates. Now, when we get into combinational circuits, we might end up with a symbol that looks like this. Now, what is that? Well, that's not a gate. But it does say input A has to be low and input B has to be high. Now, the way it would actually be made up would be built like this. So it would actually have the circuits for an inverter and the circuits for an AND, but they don't draw it that way because we understand ANDs and ORs. And we understand that is not a basic gate, right? You understand? So it's got to be a what? It's got to be combinational. You know, it's not a basic gate, but all your gates, whether a combinational gate, all your digital circuits, whether they're combinational logic or not, are made up of the 5 basic gates. And we'll run into this several times in this class. But we know what it is. We know it's combinational, and I know I can't say all for that guy, right? Why? Yeah, so it's got that inverter here. So what we'd say, if we call this input A, now we'd have to shift over to A. We'd say input A has to be low and input B has to be high. That's the way we would say that. Cause, to get a high. Yeah, cause the output is high active. See, there's no bubble out here, right? But those are combination logic. So what we learn is we're learning the basic gates, and we'll look at the inside of some of these guys, and just to show you that these guys are nothing but the basic gates. So if I've got a counter, it counts. It's nothing but the what? The basic gates. But what we're going to find out, we understand it's combinational, and we don't really care what makes it up. All we need to know is how the output responds to the what? To the inputs, right? So this is an OR. What does the OR say? Any high equal to high. So we'd start off here, 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 right? And then I'd go down, and then I would just start following the input. Are we okay? Yes? What does this guy say? All highs equal up. Did I miss one? Huh? Yeah, the first one's wrong. Good job. Any more? We okay? This guy says what? Come on, guys. Good. So what I do is I just go ahead and identify what the gate says it's looking for. So here we have all those. Here we don't. Here we have all those. Here we don't. Here we don't. Here we do. Is that right? And what does this guy say? And what would be the complement? Any high would give me a low, right? Just do what? Just flip everything. So it's very similar to what we call pushing bubbles. We say all. Anytime we see this D shape right here, and all them, we say all, and then we say lows. Why do we say low, Michael? Oh, the bubble, right? Did you do your worksheet? Let me see it. Sorry. I'm giving y'all all the answers. see it. Hold on. Is that okay, guys? Now this gets a little difficult. Why? Yeah, because all inputs. So this is a 4-input NAND gate, and it's looking for highs. So let's go across the first one first. Forget all of them. So right here we have all highs. I think the only place we have all highs again is this over here. Did I miss any? Huh? I did miss any? Okay. So all highs equal to low, so we start off here. So all highs, here's all highs, right? Equal to low, I'm sorry. I got it backwards. Yeah, I inverted it. So I did an AND gate. I saw an AND gate in my head. Thank you. So it's opposite of what I drew, right? Alright guys, we okay? Okay, here what we're wanting to do, I think it said, come up with what we're supposed to put on the input to get the output low. So what did I have to put on the input over here to get this output over here to go low? Yeah. You mean here? This OR? Okay. What about CD? So let's just, CD would be what? And EF? And what would I need over here? Now this is the same circuit, y'all understand that? One of them's drawn in all positive logic, one of them's drawn in active logic. So what we wanted to get across is which one would be easiest to do. The one on the right, because the one on the right tells me I need lows and I need highs. The one on the left, I had to figure it out. Right? Y'all understand? And this is what I was trying to show you about active logic. Active logic, the gates are drawn to show you what the circuit is looking for. So notice both of them have the same, require the same inputs. But the one on the right should have been easier to figure out because it's active logic. And this is where you can tell right off the bat. Here I have a high active input being fed by a low active output. When you see that, you know odds are it's not active logic, right? And now you got to figure the circuit out. You got to figure out what it's supposed to do. My mouse don't like this table up here. This would be a symbol for an exclusive OR, right? So how many inputs could an OR gate have? 2 or more, right? How many inputs does these exclusive gates have? 2. That's what they're doing, they're comparators. Now what this guy here shows me, what I get if they're not equal. So we should expect this guy to give me a high when they are not equal, right? So where would I start off here? Here they are equal, right? Is that right? Yeah, you notice all these only go low for one time. Or I'm sorry, they only go to the one state. They only switch states once. Okay, so this is an exclusive OR. So what would we do? Right here it's 0.3. Huh? Oh, I'm sorry. I was just showing across waiting to say something. So I didn't get credit for that. So y'all tell me, all I'm gonna do is I'm gonna start drawing. What we start off with? Okay. Good. Huh? Well, no, this is not an any. This is not an all. This is a combinational logic gate. As soon as we say combinational, then the any and the alls are out to lunch. They're gone. The only time the any and alls come into play is on our basic gates. Okay. This gate said this is an exclusive OR. It's not an OR, it's an exclusive OR. And we showed y'all the circuits that made up this thing, right? You understand? So this is our first combinational logic circuit that has its own gate. So this guy, you got to know how it works. There's no any and there's no all. So what the exclusive gates do is the exclusive gates are basically comparators. They tell us when the two inputs are either the same or if they're different. And the way the symbol's drawn, there's nothing I can do about this, guys. But this shows us what we get when the two inputs are not equal. So what that gate right there is saying is the input would be high if they are not equal. I'm sorry, the output will be high if the inputs, and it should be the two inputs. These guys won't have more than two, right? So if we came up here and identified when they're not equal to each other, right, that would be here and here. Well, it'd probably be easier to identify when they are. No, because that's what it said, I'm sorry. And here they are equal. Here they are equal. So this guy here is high and this is high. This is low and this is low, right? Now, right here it's what? Low, I'm sorry, and high. And then this right here would be high and low. So we can't use the any and all here, Brian, and that's just something you learn about this game. And of course, it's spread out exclusive OR, but normally we use X, and then for exclusive, and then OR. That's a short method of representing. So this is an exclusive OR. And so I usually do that, indicating what we get if they're not equal. Okay. So when are they? So here they're what? Here they're not equal. Here they are equal. Here they're not equal. Here they're not equal. And here they're not equal. So I'd start off what? High. Mine gets worse every time I draw it. So here they're not equal. Here they're not equal. Oh, I'm sorry. Oh, they're not equal. Here they're equal, right? Here they're not equal. Here they're not equal. Here they're equal. And here they're not equal. What? Oh, yeah, sorry. You got your worksheet? Okay. Did I miss any more? Yeah, what I'm doing is marking when they're not equal. That's why I put the X's. So we start off, what will we start off, guys? You do the first one, that's the easiest one. That's just an inversion. Okay? Now this is an exclusive NOR. This means we get a low when they're not equal. So here they're not equal, here they're not equal, here they are equal, here they are equal. Here they're not equal, right? I miss any? Thank you. Is that okay? Okay, so this is going to be, alright, start off, what do we got? What we got? Well, what we got? Okay. Are we okay? So what I'll start off with here, let me draw the symbol of it. Right. Start off with a high. Okay, right here. All the way across. Huh? No, these are not equal. So they're not equal here. They're not equal there. They're not equal here. And they're not equal there. Here they're both what? Here they're both low. It might be better to do it like this. So here I got a high, low. Here I have a high, low. Here I have a high, low. And here I have a low, high. Right here I have a what? Low, low. So this guy here will go low if we have a low, low, or if we have a high, high, right? Oops. I should have kept that. I could have used that for a key, but so that would probably make it a little better to see. So here we have a high, high. Here we have a high, high. Here we have a low, high. Here we have a high, low. And here we have a low, low, right? So what do I start off with? Right? We okay? Here they're different. Here they're different. Here they're different. Here they're different. Here they're the same, right? I get that, guys? We okay? Huh? No. It's if the inputs are both low or the inputs are both high, the output will be high. So we could come up with an expression. These guys look for if the inputs are the same or if the inputs are different. So here they're the same. Here they're the same. So this says if they're different, I'm going to get a low. If they're not different, I'm going to get a high. So here are they the same? High, high. Right? See that, Brian?
Yeah, I got that. I'm trying to get it.
You can't. It's a combination of logic gate. Right? Understand? That'd be like looking at a counter and trying to come up with a high, all, and any. There is no all and there is no any. That gate this guy looks for equality or looks to see if they're the same or different. So if you wanted to come up with a phrase, you'd say, if the inputs are not the same, the output would be low. If the inputs, so if you say that, then you say, well, if the inputs are are the same, not high, are the same, then the output would be high. That's why you flip this thing around.
So that was the input on the
No. That's why I put this thing over here. And that's what gets confusing about it. You know what this symbol right here means? Not equal. So what it says is that if the inputs are the same, I get a low. Right? You understand? I'm sorry. If the inputs are, you got me confused. If the inputs are different, I get a low. So if the inputs are different, I get a low. And that's why when I draw these things right off the bat, I put this sign right here. I put that right there. I put them every time. Y'all see me do that. Just so now I know if the inputs are right, y'all understand what they're saying. So if the inputs are not the same, I get a low. So here, the inputs are not the same. So right here, I got a what? Low. Right here, I got a what? A high. They're not the same, so I get a what? I get a low. This is a high and this is a low. They're not the same. I get a low. Here's a low and a low. They are the same, so I get a high. So here we're saying we can't use the alls and the any's here. So I come over here and I look at that symbol and I would say if the two inputs, so you can't put equals, are not the same, the outputs will be those. That's what it says. Now I don't know how you would come up with that. Huh?
Or it is. I mean,
Okay, so draw the symbol. That's the symbol. It says, okay, this says if they are not equal, I get a high. If the inputs are not equal, I get a high. That would probably be the shorthand method. If the inputs, because we're always going to have one, two, and that's why we're comparing. So this symbol right here would say, yeah, if the inputs are not equal, we get a low. And then you got to figure out, okay, so what would it be if they are equal? And so what I know is I know that these guys right here are comparators. So they're either going to tell me if the inputs are what? Equal or not equal. And that's all of them, guys. And what do we use exclusive ORs for? What do we use exclusive gates for? We can use them for comparators, right? Compare. We can use them to do math, right? Well, we can make adders. We can make them add. Can't make them subtract, but we can make them add. But we can add. We can subtract by addition, right? You understand that? Y'all learned that in algebra, right? Y'all didn't learn that. It's dealing with sine numbers. Well, what did you learn about sine numbers? Change the sign of the subtrahend and add, right? So we'll show y'all some techniques for what the things really use, which is really strange. So let me bring my calculator up. And I'm going to put it in Programmer's Calculator. And I'm going to come up here and say a -1. And then I'm going to convert that to binary. Of course, it's already got it down there for me. That's a -1. Can y'all see that? It's all what? It's all ones. And if I take that and swap it back to decimal, it says it's a -1. Interesting. So that's the worksheet. Any questions on that, guys? Like I said, I didn't have a key to give y'all out.